Hello, this is Sadashiv Fadnis, Product Marketing Manager for Rubidium signal generators here at Amritsu. In this video, I will be demonstrating a simple and inexpensive method to make amplitude response measurement using analog sweep option and frequency marker feature in Rubidium. We will use a simple oscilloscope that supports XY mode and an Amritsu RF detector 75KC50. 75KC50 is a 40 GHz detector with a dynamic range of -30 to +20 dBm. Here is the setup to make amplitude response measurement. RF output of Rubidium signal generator is connected to device under test or DUT, which is a bandpass filter centered at 1.85 GHz. The output of DUT is connected to input of 75KC50 RF detector. The output of the detector is connected to channel 2 of oscilloscope. Rubidium's horizontal output available on the back panel is connected to channel 1 of the oscilloscope. Ethernet ports of Rubidium and oscilloscope are connected to my PC through an Ethernet switch. This enables me to run remote GUIs for each instrument on the PC so that I can control and configure Rubidium as well as display waveforms of oscilloscope. Here is the PC screen with the two remote GUIs. This is Rubidium remote GUI. It pretty much mirrors the GUI on the front panel of Rubidium and allows me to configure parameters just like on the front panel. This is the oscilloscope GUI. The oscilloscope has a VXI11 server, and a snapshot of oscilloscope's display is published on a page every 10 milliseconds or so. This GUI on my screen here accesses that page. We are going to access this page to look at waveforms and to measure amplitude response. We'll first set the output level of Rubidium. So let's go over to the screen. The level currently is +0 dBm, so let me set it to something much higher than that. Let's set it to +13 dBm so that we have enough power to make the measurement. +13 dBm. Okay. We will then move over to the sweep menu. This is the main sweep menu, so let's choose analog sweep. This is the setup screen for analog sweep. Now remember, our DUT is a bandpass filter centered around 1.85 GHz with a pass band of 200 megahertz. So let's first set up the start point, and I'm going to set it to 1.7 gigahertz, closer to the band edge of the bandpass filter. And I'm going to set up the stop point to say 2 gigahertz, again closer to the higher end of the stop band of bandpass filter. We will also set the trigger to auto. There are several options here: auto, single, or external. We'll be using auto, so which means the sweep will be triggered internally continuously. There are two more settings to check before enabling the analog sweep. So let's go to level menu, and within that let's go to setup menu. Check the retrace RF setting on this screen make sure that it is set to off. Retrace RF is set to off. And then we move on to the system menu and click on the config sub-menu within the system menu and set the ramp rest to start. There are two choices here, start or stop. Make sure that it is set to start. Now we will go back to the sweep menu again. So that lands us in the trigger sub-menu. So we will go up to the setup menu. Earlier we had set the start and the stop points. Now let's set the sweep time. Let's set the sweep time to say 100 milliseconds, which is 0.1 second, which is fast enough to make some real-time measurements. Okay, so with these three settings, I think we are good to enable the analog sweep now. When analog sweep is enabled, Rubidium outputs a voltage that is proportional to instantaneous frequency between start and stop points of the RF sweep. This is called the horizontal output signal. It is a ramp signal with a peak of plus 10 volts. As mentioned while describing the setup, we have connected this horizontal output signal to channel 1 of the oscilloscope. We have also connected output of RF detector to channel 2 of the oscilloscope. Let's take a look at these two signals on the oscilloscope now. Let me take a snapshot. Okay, so what you see on this oscilloscope display is the horizontal output at the top here. This is the beginning of the ramp, this is the end of the ramp, so which means this is the beginning of the sweep and this is the end of the sweep. I have set up two markers over here, which is, marker 1 is at the beginning of the ramp and the marker 2 is at the end of the ramp. And the delta between these two is 99.2 milliseconds, which is just a bit shy of what we had set on Rubidium, the sweep time that we had set, which is 100 milliseconds. The markers are showing us 99.2 milliseconds, pretty close. The waveform at the bottom here is the RF detector's output, and you can see that the RF detector goes low whenever it detects an RF signal, and then goes high when the signal goes off, right? So the output of detector is inversely proportional to the RF signal that's coming in. So what we will do is we will for this channel 2 waveform, we will invert this waveform in the oscilloscope. So I have set the oscilloscope channel 2 to invert mode. Let me take a snapshot again. Okay, so you can see now that the channel 2 is displaying positive voltage whenever it detects an RF signal, and then a low whenever the RF signal goes off. Right, so this is the right polarity. So we are going to use these two signals, the signal at the top, which is the horizontal output, and the signal at the bottom, these two in XY mode. So we are going to set the oscilloscope in XY mode The ramp signal will be the X signal, so which means it will drive the horizontal axis, and then this channel 2 output will drive the vertical axis. So let's set the oscilloscope to XY mode, and what this should display once you set the oscilloscope to XY mode, it should display the amplitude response of our DUT, which is the filter. So I have set the oscilloscope to XY mode. You may have to make some adjustments in terms of each of the channel offsets so that you can get the amplitude response in the center of the screen. But having made all that, let me take a snapshot of the oscilloscope page. Okay, so here you see the amplitude response of the filter essentially. As I was mentioning, the ramp signal, the horizontal output signal, is driving the x-axis in the XY mode, which is channel 1. So it is set to 1 volt per division here, and as I had mentioned before, the horizontal output is plus 10 volts at the peak. So when you set the channel 1 to 1 volt per division, and you can see there are 10 divisions here. So this is from bottom of the ramp to the peak of the ramp, so which is driving the horizontal axis uniformly. And then on the vertical axis, we were using for the Y, for the Y signal, we were using channel 2. So the channel 2 signal was the RF output from the detector, and this has been set to 200 millivolts per division, and there are about 4.5 divisions. So the output of the detector gives you almost 900 millivolts, and remember, we have set the output level to plus 13 dBm, and at plus 13 dBm the RF detector is giving you nearly 900 millivolts of output, and when in the stop band it's giving you nearly 0, right? So this is your pass band response, and these two are your stop band skirts, right, on both sides. Now the one additional thing we could do with this measurement on the scope is we can also enable frequency markers. Rubidium generates frequency markers in the analog sweep, and we can enable them. So let's go and enable the frequency markers. You can set them on the frequency menu. So let's go to, this is the frequency menu, and then go to markers, and then if you choose this next screen, you can set the frequency for the markers. And I have already set some markers here, and as I had mentioned, the center frequency of this filter is 1.85, and the band edges are 1.75 and 1.95. So let's enable these three markers. So which should appear at the band edges and at the center. Let's go back here again, and let's enable the intensity marker, and let's take a snapshot to see how the markers show up. Okay, so here you see the three markers. one at the lower end, which is 1.75, one at the higher end, 1.95, and one at the center, right? These three. But you could set the markers wherever you want. For example, I could set some intermediate points, say 1.8 and 1.9. So let me enable all these markers, go back, and let me take another snapshot here. So you see all the markers that I have, all the 5 markers that I had set. So this is 1.75, I think, 1.8, 1.85 in the center, 1.9, and 1.95. So you can enable the markers, and you can use those markers to set your pass band and the stop band when you're tuning the filter. And the sweep speed is fast enough. It's about 100 milliseconds, so that you can continuously, so it updates. If you see on the oscilloscope, it keeps on updating the screen, and I can update here on the GUI once again, and you can see this response. So this is how you can see, or you can measure amplitude response of a passive device or an active device using a very simple setup, right? You use just the most inexpensive oscilloscope along with the analog sweep in Rubidium, and you can make this measurement. Now the question is, what is the dynamic range of this measurement? When this signal hits very zero or very low value, and when the signal hits very high value, what is the delta between these two? So if you look at the RF detector specifications, RF detector gives you nearly a few millivolts, like 5 millivolts signal at minus 30 dBm, when the signal is, when the RF input to it is minus 30, and it gives you nearly 1 volt output with a peak of plus 13 or plus 15 dBm. So it's plus 15 and minus 30, so you're getting a dynamic range of 45 dB almost with this setup. So it can't get anything simpler than this. You're just using an oscilloscope, an inexpensive oscilloscope, an RF detector, which is also inexpensive, and analog sweep of Rubidium. A very simple way to make amplitude response measurement.